Thank you. So I hope you're all up to speed with cache side channels, because we're going to skip the background because of time constraints, and we're going to start off with the novel part. Now, does this work somehow? No? Continue? No? Maybe the other one. What? Do I have to? No. It's the green button, right? Doesn't do. Yeah, there we go. No. Back doesn't work now anymore either. How does that? Whatever. Okay. Intel introduces some new instructions quite regularly, and the wonderful part about this, I personally love to look at them. And one of them is the CL-Demote instruction. If you've ever heard of CL-Flush, CL-Demote is very, very similar. It's a very recent instruction, available mainly on Xeon CPUs, so server stuff. And in essence, it moves a cache line from a higher level cache, so L1, L2, to lower levels, L3, further away from the core. So for that to actually work, the cache line has to, of course, be accessible to whoever executes the instruction. Okay. And since this sounds very similar to CL-Flush, we can do some similar stuff here. So here's some interesting timings. So the left graph is just timing the CL-Demote instruction. And depending on if the cache line is in the L3 over here or the L1 over here, the timing differs. So if it's in the L1, CL-Demote takes longer because it has to move stuff to the L3. If it's already in the L3 or not in cache at all, it's significantly faster because it just has to do less stuff. On the right-hand side, we have the classical thing, the difference between L1 hit and the L3 hit, of course, pretty large. And the L3 hit measurement here is after executing the CL-Demote instruction on some cache line. So we move it into the L3, and then if it's accessed again, it takes significantly longer to access. Okay, we have one more timing difference that we noticed with this instruction, and this is like a very tiny difference. So for some reason, if you execute CL-Demote on a cache line that is currently, that it doesn't have to be anywhere in the cache, but if the cache line would map into an L3 set, so into the same part of the L3, as something else that is currently accessed, you get some slower execution times for CL-Demote. It's this part up here in red. Presumably, this is some sort of contention, and for some reason, CL-Demote accesses apparently the L3 without having to do anything. We're not sure about the actual reason for this, but we can detect some like operations even other cores do on the L3. Okay, so what can we do with this? We of course built some new attacks. Two of those are very similar to Flush and Reload and Flush+Flush, if you know them. So the first one, Demote and Reload. So we have the attacker, which just executes CL-Demote on a cache line, moves it to the L3, and if now the victim accesses this cache line again, it gets moved back up into the L1, and if the attacker later on measures the access time for the cache line, it will of course be so it will of course be lower, so it will be faster to access the cache line if it is in the L1. And if it wasn't accessed by the victim, it's in the L3, so yeah, you can detect the difference. The other side is Demote+Demote, so the attacker only performs CL-Demote on the cache line. And depending on if the cache line is in the L1 or not in the L1, the timings will differ again. It's slower to move a cache line from L1 to L3. And lastly, we have something that we call DemoteContention, where the attacker is like on a completely different physical core, just demotes a cache line, which doesn't have to be present in the cache hierarchy at all. And if the other core now somehow accesses the same cache set in the L3, so the same part of the L3, the attacker can detect that through contention. All right. So now we have new attacks. Let's do some analysis of not only our new attacks, but also old attacks. It's like the main part of the paper. We look at old cache attacks and properly compare them, because previous papers did their own custom implementation of these attacks. Those might be optimal, suboptimal. Didn't really analyze all aspects of them. So we're doing that. So we analyzed 7 cache attacks, a few existing ones, Flush and Reload, both on SMT, so same core, and cross core. Might sound very similar, but you get some very different characteristics depending on where attacker and victim are running. We have Flush and Flush, also as SMT and cross-core. We have Prime and Probe on the L1, Evict and Reload on the L1, and of course we have our 3 novel attacks. Yeah. And we tested all these things on 2 recent Intel microarchitectures, Sapphire Rapids and Emerald Rapids. They're like the 2 most recent Xeon microarchitectures from Intel. And yeah, we evaluated this very extensively. So we came up with 9 metrics to compare them. The hit-miss margin, so how much time is there between when you detect an access and when there was no access. There is the temporal precision. That's like how long does it take to detect an access. Spatial precision, no, temporal precision was, yeah, exactly. So spatial precision is like how accurate can we detect an access? Is it just, can we detect an access in a cache set? Can we detect the exact cache line? Stuff like that. Topological scope, does the attacker need to run on the same core as the victim? Does that can it be a different core? How long do the attacks take? Blind spot size, we'll get into that in a second. Channel capacity, like if you build a covert channel with it, how fast is it? How much data can we actually leak? And noise resilience. No, there's actually one more. Noise resilience is like what happens if there's noise in the background, how much worse does it perform? And last, we have detectability. We use performance counters for that. How well can we detect the attacks? Okay, since this is a short presentation, and those are a lot of things, we're going to look at these 3 for this presentation. If you want to see the rest, look at the paper. I also have some backup slides if you have questions about the rest. But let's keep it at that for now. So blind spot. So typically, for some of those attacks, you have some setup phase. Like for flush and reload, you first flush the cache line, and afterwards you access it. If now the victim access happens at the wrong time, you might not actually see the victim access. Like if it happens right before resetting the cache state with CL flush, then you flush the cache line and you will no longer notice if the access occurs. And we measure this by simply doing victim accesses at a random time. And in the background, the attacks can run continuously and try to detect the access. And in between the attacks, we also added some sleep time, and we varied that, and just to see how that would affect the blind spot size. And we have a wonderful graph for that here. So on the very left side, you see how large the blind spot of the attack actually is relative to the actual attack time. And for Flush and Reload, it's very high. It's like about 80%. And for the newer attacks like Demote+Reload, it's relatively low. And there are 2 attacks missing here, which is Flush and Flush and Demote+Demote. And we actually found out that they have no measurable blind spot at all. They detect all accesses, which is nice. And there's also one exception here. All of them go up with an increased sleep time between attacks. One of them go down. One of them goes up, which is DemoteContention. And the reason for that is we try to exploit this contention behavior. And if we add some sleep time, then we will hit the contention less often, because we're not measuring actively. Okay, temporal precision. So in essence, we just do a memory access at some random point in time, again. And we try to figure out how long does it take for the attacker to detect the actual memory access. And this can vary depending on the attack. So here for Flush and Reload and Demote+Reload, it looks relatively similar on SMT. For Flush and Reload cross-core, for some reason, this is a lot more like at one single location. It's overall slower, a little bit slower, but it's less spread out, which can be advantageous for some attack, like some inter-keystroke timing attacks, for example. Also down here, Flush and Flush, Demote+Demote, and Flush+Flush SMT. And here we have also some special case, which is DemoteContention, since we're exploiting in contention behavior, which happens exactly at that point in time. We, of course, have this one spike here. Okay. Very quickly, covert channels. We built some covert channels with all of our attacks. And the basic setup was something like this. So first we have this sender, which sets up the cache state, and afterwards the receiver, which just performs the attack. And we have these 2 variables here. How long does the receiver wait before trying to detect? and the time window right here for sending a single bit, and we vary that a bit. And those are the overall capacities for them. So DemoteContention is relatively slow because there's a high error rate. Flush and reload, SMT, and regular flush and reload up here. Evict and reload is around here. Prime and probe here. Demote+Reload a little bit higher, 6 Mbit per second. Flush and flush SMT is very fast. Demote and Demote also at around the same location. And flush cross-core is also a little bit faster than that. For covert channel, we put some special cases in there. We found we determined that if the victim does the flush or the demote, we can build significantly faster covert channels, and then the attack the receiver just does the memory access. So we have 2 more cases which we called optimized flush and reload, which is right here, and we have optimized demote and reload, which is at around 17 megabits per second, which is way faster than the rest. Okay, more metrics. Just look at the paper. We also have some attacks. The first one we're going to skip here is an AES T-table attack. But we also have some other things. So something interesting in the manual we have for this instruction, for CLDemote, is we have only one exception that could be triggered, which is the lock prefix. But if you're keen on x86 instructions, you might know that they typically also do page faults when you do a memory access. In this case, CLDemote never triggers a page fault, which is weird. So you can demote instructions like memory locations that aren't mapped or accessible to you. So we did a KASLR break with that. So we executed CLDemote on cache lines that are in the kernel, where we would expect like kernel text segment to be. And then we just measured how long it takes. And it's significantly slower if there's nothing mapped there, and significantly faster if there's something mapped there. And the reason for that is the TLB. If a memory location is if like the translation for a page is in the TLB, it's significantly faster to determine if the demote instruction should work or not. And not mapped pages are not in the TLB, so they take longer because they have to do a page table walk. We also have something like this for this other CPU. This is an Intel Core i7, and this is a desktop CPU that doesn't support the instruction. But the attack still works. You can still break KASLR. And Intel claims that if this is not supported instruction, it should be treated as an op. And apparently, Demote is treated as an op, like it does nothing important. But on pre-12th gen Intel CPUs, it also does nothing. But on more modern CPUs, it actually does the TLB lookup, but nothing else. Yeah. Okay, to summarize what we did in this paper. So we introduced 3 new attack primitives. We performed a systematic analysis of 7 attack primitives with 9 metrics. We compared these with AES T-table attacks, first and last round. We compared them with inter-keystroke timing attacks. And we also did some 2 attacks only with our new attacks, which is a KASLR break and colliding power, so power analysis. And yeah, also want to thank our funding partners, and that's it. Thank you.
Okay, we have time for 1 or 2 questions. If you have any questions, please come in front here to the microphone. And in the meantime, maybe I have one. So the benchmarking evaluation suite for the different cache side channel attacks is very cool. I guess you did it on x86. How much would you think is the effort to port it over to other instruction set architectures?
So the effort to port it over, since most of this is just C code with only inline assembly for the actual attacks, it's very little effort.
Okay.
You could just do it directly with the current script. So yeah.
Okay, very cool. Well, okay, if there are no questions in the room, let's thank Fabian again.